Hello, class. Today we're going to be talking about kind of the overview of this specific section. I was having trouble finding specifically something that went over it in enough detail, but not so much that it was just overwhelming. There's a lot of different vocab and different like mathematical things that happens here in this specific unit, and it can be overwhelming. But something that is like really great is if you can do kind of the mathematical problems from the last section. Projectile motion, you're actually just gonna, like, instead of doing just one using one equation for one problem, for each problem you'll do in projectile motion, you'll actually just use two equations instead. And what's kind of nice about that is, so you're not really learning new things, you're just learning like how to do the same thing but applied in like a different way. And so what we're gonna do is we're gonna cover a few different topics. So this is object and free fall, projectile, scalar quantities, vector quantities, resultant, components, independent, dependent, and then an example projectile motion problem. This example too is gonna be the one that I expect you to know how to do later on. There might be another one that I make you do, but there's gonna be an equation for that, so you won't really need to worry about that. But without further ado, let's just jump into it. So we have here object in free fall, an object that undergoes motion due solely to the force of gravity. And that's like the important part, right? So if you have a person and they're just like standing there and they like drop a ball and it falls, right? This object is in free fall. And the reason we just need to talk about this is because a projectile is something that's actually just very similar. So some things I want to mention about gravity. Pretty much for our class, the value we use for gravity is 10 meters per second squared, which is to say that if you're anywhere on Earth, right, here's the Earth, there's Florida, and there's like, I don't know, Mexico or something, and then Baja California. There we go. So if you're on Earth, anywhere on Earth, objects are going to accelerate downwards towards the center of the Earth at about this rate. Meaning, if you dropped an object from rest, meaning it has an initial velocity of 0, right? So its initial velocity, VI, equals 0. And then you let it drop for like 1 second. So our time is 1 second. The velocity at this point is going to be 10 meters per second. Let it drop for another second, and the velocity will be 20 meters per second, and so on. It'll keep increasing for every second that it drops. Keep in mind, in real life, when we drop an object, it kind of slows down because of air resistance. But since we're focusing on physics, and physics focuses on like the perfect real world, we don't have to worry about air resistance. So this is basically the value you can always use for gravity on Earth. So if we ever do a problem where we're not on Earth, that's where you might be uncertain as to what gravity would be. But anywhere on Earth, you're good there. So when we talk about objects in free fall, usually it's just things dropping. And sorry for that loudness, was the train passing by. When we talk about projectile, right? Says an object that, once projected or shot out or thrown, continues its motion solely by its own inertia. We'll talk about that in a second. And the force due to gravity. So first, inertia. This is actually one of Newton's laws. And it basically just states, and maybe you've heard this before, that an object in motion will stay in motion, or an object at rest will stay at rest, unless acted upon by an outside or external or unbalanced force. And so basically what this says is, let's say we're in space far enough from all types of gravitational influences, right? Just have this ball, and let's just say it's just moving at some rate. Well, inertia, right, the law of inertia, Newton's first law, would state that it would just continue on going at the same rate. It would never slow down or speed up, just move at the same rate for an infinite amount of time, unless there's a planet maybe you got by, then it would actually start going quicker and quicker towards it. And so that's all inertia means. So when we're talking about projectiles, we're talking about things that get shot out. The reason it continues forward is because it has inertia. That's all you need to know about that. I'm never going to ask you a question about inertia. But now let's look at, for example, something like, I don't know, say we have a cliff and we have a projectile that gets shot out horizontally, right? So that means its initial force gets pushed off that way. What inertia is going to help us with is that over time, right, this object will drop because of gravity. But notice, right, it still kind of continues forward no matter what, right? And that continuing forward no matter what is due to the inertia of the object. And this is a little misleading because later on you'll find out that if I drew these at 1 second intervals, which I already realized I'm starting to use like vocab that might be confusing, like interval and things like that, they would actually travel out the same horizontal distance every single time, right? So if this was equal to delta x, or just a certain distance like 1 meter, then this would also be 1 meter. From here to here would also be 1 meter, and then so on and so forth. So that's all you need to know about what a projectile is, and this is going to help us kind of later on understand something about what's going on here. So let's go to scalar quantities. It says a physical quantity, or physical quantities, measurable amounts, right? So don't let this word confuse you. Basically, if you can measure it, it's probably a physical quantity. That only have magnitude, also don't let this scare you. That word means amount, like how much. How much? For example, time, temperature, mass, area, volume. So for example, temperature, you're only going to have amount. You don't have a direction that necessarily temperature has. Mass doesn't have a direction. And you might be wondering, why am I mentioning direction? You'll see when we talk about vector quantities, right? So I didn't want to have to introduce these too much, but it's hard to get away with in this unit without knowing the difference. So vector quantities are physical quantities that have both magnitude and direction. So for example, displacement, velocity, acceleration, and force. So some of these we've already dealt with. And because they have both magnitude and direction, a really great way to represent a vector is just with an arrow, right? So we have this arrow, right? The way the arrow is pointing would be its direction. And then how long the arrow is, right? That can represent the magnitude, or the how much, right? So let's say we have a ball and it has what we say acceleration is a vector. We can represent its acceleration downwards. And we can say that this represents 10 meters per second squared. So if we were on like a different planet, you might have another ball. Let's say this planet has a gravity that is twice, so it's 2g's, twice our gravity, right? Then the arrow would still point downwards, but it would point for twice as long, or twice the amount. So this one is 2 boxes big. This next one would be 4 boxes big. So 1, 2, 3, 4. So we'd have an arrow that's represented like that. And so usually we try to draw them to scale, but the nice thing about physics is as long as you're doing the math correctly, you don't necessarily need to draw to scale. And vectors, kind of like any other normal number, like any other scalars, right? They can be added and subtracted and multiplied in similar ways. You just have to worry about direction. So real quick, let's go back to scalars. If we were to add the mass up of something, so let's say there's an object, I don't know, I'm just using spheres, right? And one of these equals 2 kilograms. I'm going to ask you, like, how much mass do 3 of these spheres weigh? And you'd simply just do 2 kg times 3, and you'd get 6 kilograms. Right? If I asked you how many, let's say this was 2, this is 4 kilograms, and then this is 6 kilograms. I'm going to ask you what's the total mass. You can do the same thing we did before, right? Because now they're not the same. But what you could do is you could just add them up. 2 plus 4 plus 6, and then you would get 12 kilograms. Now, right, super simple so far. What if I did this? 6 plus 2 plus 4. Well, we'd still get the same amount, right? The reason why I wanted to show you this is because when you add vectors, you can do the same thing. And you might be wondering, like, how does that work out? Well, let's see how this works out. So, resultant is the sum of vectors, right? The sum, right, is right here, right? We add this, and we get that. This is the sum. But when we're adding these little arrow-like things, we call that added amount the resultant. So let's just say, let's have 2 vectors. Let's say, right, there's a car. And on this car, we have, let's say, I don't know, just someone, and they throw a ball upwards, directly upwards, while the car is moving horizontally, right? So we can see that we're kind of dealing with velocity vectors maybe. And maybe I want to figure out, what is the velocity of the ball. So if we represent the ball here, we know that the car and that whole system, right, is moving as fast as the car. So let's say it's going like 20 miles per hour, or 20, we'll do meters per second to be consistent. Let's say the person throws the ball up, I don't know, maybe at 5 meters per second of velocity, right? So we have two vectors here. I'm just going to redraw this one because it looked ugly. We can actually add these vectors up. And the way that we do that is simply by taking one of these vectors. So we'll call this vector A, call this vector B, and just kind of scooching it over. So I'm going to trace this over a little bit. We can do this with either vector. We get a vector that looks like that. And now we don't need to worry about this one. And our resultant is just going to be from our starting point, which is at this purple dot, to our ending point, which is right here. And something you might notice right away is that, well, first off, this new red one that we made, that's actually just vector B. And this purple diagonal one, that's actually going to be a hypotenuse. And not only that, but we have a right triangle, right? So if we really wanted to figure out this hypotenuse, which we may have to do later on, you would just use Pythagorean theorem, which is, in its simplest, a squared plus b squared equals c squared, where the a and b are the legs, which would be our vector A and vector B. If we wanted to add those up to find c, we would take the square root of both sides, and then that would knock this out. We would get the square root of a squared plus b squared is equal to c. Something that's nice about this is that for vectors, like if we have a lot of them, let's say we have a vector that goes up, and then a vector that goes down, and a vector then that goes right. It doesn't matter which way we add this up in, because we're always going to get the same amount. So I'm actually going to give myself a little bit more room here. So each of these are one, let's say it's one box in length. So let's say this is our starting point, and we have one down, one up, one across. So let's go one down, we go one up, which is on the same part, and one across, and we get here. If we do this in red, let's say we go up instead this time. We go one up, one down, one across, still have the same endpoint. What about if we do, we can do one across, and you're like, oh wait, we're already there, what's going to happen? Well, we go one down, one up, we end up at the same point. If we do it one last time, let's do one up, one across, one down. Our resultant, no matter what order we add these vectors in, is always the same amount. So beforehand, I told you that when you add scalars up, it doesn't matter what order you add them up in. In the same way, when you're adding vectors, the order doesn't matter. However, how you add them matters. So for example, let's say we have this vector. It goes up, we have one that goes across, and we have one that goes up again. Our resultant is going to be from our start point to our end point. And so if we drew that, now it's like a little confusing because you're like, well, I don't have a triangle anymore. But the thing is, we do have a triangle, because what we can do now is if I were to throw, let me get something a little bit thinner here, a coordinate system on, like a really small one. Okay, let's do that. Notice how I can actually drop this down. And we see that this is 2 units high, and then it's 1 unit in length. And look, you can use this A and this B to find the length of this one, which is C. So if I wanted to do this, we'd have 1 squared plus 2 squared, take the square root of that, and that would give us our C. So what is that? 1 plus 4 we get the square root of 5, which off the top of my head, I have no idea. It's something that's a little bit bigger than 2, which would make sense. So that was a lot, and I'm hopefully feeling that, I hope that you're not feeling so overwhelmed, but this is basically just saying, right, when you add vectors up, what you add up is called the resultant. And what's really nice is it says components, parts when added make up a vector. We actually just did that. So for this previous question, this 2 and this 1, those were the components, right? We had something that was like, vector that was like, I don't know, do this one, right? Say that was the resultant after you added the vectors up. If you wanted to break that down, we'll use a different color here. Right? You would just trace that thing downwards, trace it across, right? And then you'd see that this is 2 units wide and then 2 units high. And those are your components. And then if you want to find how long this guy is, you just use Pythagorean theorem, right? So not too bad. And the reason why we're talking about this is it has to relate to projectile motion, because what you're going to notice is when you launch something, like let's say off the side of a cliff, right, it's going to have a horizontal vector, but it's also going to have a downwards vector because of gravity and how that's working. So over time, this downward one actually grows, but we'll talk about that a little bit more later. So let's go to independent and dependent. And I hope I don't run out of room here. Okay, we're doing good. So independent, when the manipulation of a variable doesn't affect the outcome of another. So let's give a very stupid but easy one. If I change my eating habits, I might ask a question, does that affect the length of a day? And you're gonna say no, right? That doesn't, I mean, it doesn't even make sense to compare those two, but that's because they're independent of each other, right? If I change one, it doesn't affect the other one, right? Whereas dependent, right, means that they do affect each other. So we'd say, does changing my eating habits affect my weight gain? And then you'd actually have to do a study, right? Because when you eat things, that's how you gain weight, right? So we're literally asking the question, if we change how we gain weight, does that affect our weight? And yeah, it looks like they would be dependent of each other. And so the reason why I want to talk about these two is really simply because vectors that are pointing in different directions don't affect each other. And when I say different directions, the ones I'm specifically talking about are the ones that line up on our coordinate planes. There's actually more to this than I'm going to talk about, but all you need to know is that if you have a rightwards facing vector, so something that maybe looks like this, and you have an upward one that maybe faces like this, I can manipulate this one, right? But it will never change how this one acts. Or we'll call this A, we'll call this B. I can manipulate B, and then I'll never change how A acts. However, let's say I had a vector A right here. We'll call this down one vector C. This is A and this is C. These two do affect each other because they're pointing on the same vertical axes. Whereas if I had, this is my vector B, if I had something that was like that, we'll call this D. These would affect each other. Dependent ones would be essentially, right, these guys right here. So vectors that point either both vertically, they do affect each other, or both horizontally, they do affect each other. But if they point perpendicular to one another, right, perpendicular being they are 90 degrees from each other, right, those do not affect each other. And this is going to come into play with our example problem here. So let's say, for example, and I was already alluding to this many times, I have a ball. It just gets kicked off exactly horizontally. Exactly horizontal. Let's say with a velocity of 2 meters per second. Okay, let's say this is a height, this cliff is a height of 10 meters. And maybe the question we're asking is, after this gets kicked off, how far out does it land later on? So what is this displacement here. We'll call it our change in x. We'll call this one, and now we're differentiating our change in y, our delta y. And if you're confused by this triangle, don't worry about it too much. It just means it's more of just a physicsy term, right? How much you're changing your displacement. So what's really nice about this is that as this ball moves horizontally, it is never going to change how much it moves, well, horizontally, right? Right. So these distances are the same. These horizontal distances are the same. And these horizontal distances are the same. And this is like every second, right? And so knowing this is actually very helpful because it will speed up downwards, right? Because of gravity, right? It's going to have maybe a little vector here for velocity, an even bigger one here, and then an even bigger one here. And then just before it's the ground, right, it'll have its like biggest downwards vector. But the horizontal one, let's make this a little bit smaller too. Let's make this like that. It'll always stay the same, no matter what. The other one may grow and get bigger, but doesn't change how much it moves horizontally. And for now, if you're still confused by this, I'm gonna have a bunch of other videos that kind of explain this phenomena. But for now, we're just gonna go through this practice problem. So something we're gonna wanna do is we're gonna wanna break up our horizontal and our vertical vectors. So I'm gonna make a column, 2 columns actually. This is gonna be our vertical stuff, y, and our horizontal stuff, x. So I'm gonna write down every single variable you can have in the y direction, every single variable you can have in the x direction, and you're gonna see a couple patterns. So let's start with the x, because the x is easiest. Well, first off, we have our delta x, right? This is how far it travels horizontally. We have our velocity in the x direction. We'll just put vx for now so we don't get confused. It's how fast it's moving in the horizontal direction. And then we have our time, how long it travels for in the horizontal direction. So something that's great about this is that gravity doesn't affect projectiles in the horizontal direction. So there's no acceleration. This thing never gets faster moving horizontally. And we'll discuss that more and how that works later. For the y direction, though, the vertical, we're gonna have a delta y, which is comparable to our delta x, but it's only our vertical distance. We have our initial velocity, right? So this is how fast it's moving in the y direction at the start. We have our final velocity in the y direction. We have as well, we have gravity, which is always going to be either positive or negative 10 meters per second squared. Negative just depends on which way you point for positive. It can be down or up. And then time, this is really nice. But these two are always going to equal each other, right? Because this is the time it takes for the projectile to hit the ground later on, and that's going to be the same. And so this is actually going to be our connecting point that makes solving these problems easier. And if I'm asking, what is delta x? That means you're trying to solve for this guy. But luckily, we can already plug some things in. Our Vx is 2 meters per second. We don't know our time, but once we figure that out, then we can figure out our delta x. We're going to look at our y side. So our y, if we were really to look at it, our projectile starts up here, and then it moves downwards, right? Moves downwards over here. So it actually has a negative 10 meter change in y. We'll put negative 10. If it's negative 10, that also means our gravity pointing downwards is also negative, right? Our initial velocity in the y direction, throw little y's there, is actually going to be 0. If we're kicking something perfectly horizontal, that means for the moment we kick it, there is no downwards velocity. So initially we just have 0. The nice part about this is we have an equation that only needs delta y, v, and g to solve for t, right? And that equation, we don't even need to use this guy. Who cares about that? Looks like this. It is, so your distance, your change in distance, we'll say it's delta y, is equal to initial velocity multiplied by time plus 1/2 times the acceleration times time squared. So let's look at this and kind of break it down. This part cancels out because we have that 0 there, right? 0 times anything is 0, so it just cancels out. Now we're left with this. Something else that we already know are these two right here. And if we know those two, that's all we need to solve for t. And that's what we want, because that t is now going to give us our t in the x direction, which will then give us our delta x. So if we plug everything in first, we have a negative 10 meters equals 1/2. Oh, this is going to be nice. Times a negative 10 for gravity. Negative because we're pointing downwards. Multiplied by t squared. We're going to cancel things out that we can cancel out. So if we have negative 10 here, negative 10 here, we can actually just knock those out. But for the sake of clarity, let's just solve for t, and then we'll get things sorted. So to get this 1/2 to the other side, we multiply both sides by 2. So we have 2 times a negative 10 now. And then we need to divide both sides by negative 10. And that cancels out these two on this side. And that will equal t squared. Now, if we look at this, the negative 10s can also cancel out because that's just normal fraction math. And so now we actually get, if we take the square root here, take the square root over here, we get a square root of 2 is equal to t. Now, I'm going to do some math real quick. So if I take the square root of 2, that equals, so our t is equal to 1.41 seconds. And what's great is that now we have that right here. So let me delete this. I don't need it anymore. So this was working in our y direction. Now we're going to work in our x direction. We have our velocity. We have our time now. And now we're just looking for delta x. And the equation that we have to solve for that is v equals delta x over t. If we solve for solve for delta x, we get vt equals delta x. We plug that in, get 2 times 1.41, and that's going to give us about 2.82 meters. And what that means is that this ball, right, after it got kicked off, went 2.82 meters when it lands right there. So this is pretty much like the standard problem that you're going to have to solve. I went through like every step like painstakingly. So once you kind of catch on to how these problems work, it'll actually become a lot easier. So remember, this was a summary of kind of all the things you need to know. There's going to be a video, actually multiple videos, that you'll have to kind of watch and dissect and make some observations on to kind of more clearly understand what's going on here. So if you are confused still, please feel free to send me emails, comments, questions, whatever it is. But thanks for your time, and I hope this will be a great unit for you.